certain form of the quadratic. When we talk about quadratic equations, a lot of times they're going to look something like this, like ax squared plus bx plus c equals 0. So like what value of x makes the function equal 0? I could put a 5 right there. I could say it equals 5. What value of x makes it equal 5? But I would have to move the 5 to the other side first. So I'll often write these as like equals 0. Or I could do an a times x minus h quantity squared plus k equals 0. So I'm not saying, like, this is no longer like a model, like you saw in that last question on the test. It's not plug in any x you want and get some random y back out. It's find me the x that makes this statement true. Okay? So that's what we mean when we solve. And of course we could do an intercept form one as well, a times x minus p, x minus q, quantity squared equals 0. Okay, so it doesn't really matter what form the quadratic would be given to us. And so there's different ways for you to do this. That's what chapter 3 is all about. Well, given which form, how am I going to be solving it? Okay. Now, one way to solve is looking for it on a graph. So if I say, when is this function equal to 0? I'm saying, like, when is its y value 0? So on a graph, I'm basically looking for x intercepts. Okay, so if I'm solving by graphing, when is f of x equal to 0, or you could say y equals 0, that means the same thing, right? At the x-intercepts. Okay, so if you're solving by graphing, you're looking for x-intercepts. By taking square roots, that's what the book calls it. I always like to say that this version of taking square roots is really one of my favorite ways to solve equations, because it's the first way I learned to solve equations in algebra or pre-algebra. When you start doing that, it's by reverse PEMDAS. Just undo all the things that are happening to x and get x all by itself. Call it like peeling away the layers of the onion, right? Just take off a layer, and then all of a sudden x is alone. Okay? So we're going to look at those two methods today. So we're going to solve this one by graphing. Negative 2x squared minus 2 equals 4x. Now notice that this one isn't set equal to 0, right? So generally, okay, depending on the form, if it's an ax squared plus bx plus c, then I'm going to want it set equal to 0. So you could take your pick. Do you want to subtract 4x from both sides? Do you want to add 2x squared and add 2? It's totally up to you. I personally might choose to add the 2x squared and the 2 to the other side, only because then I don't have all those negatives. Okay, so I like that. So make one side equal to 0. This would be 2x squared. I'm going to rearrange it plus 4x plus 2. And then I want to graph it. Well, in order to graph it, I got to know where the vertex is. So this is front page of your test, right? In the form ax squared plus bx plus c. Find the x coordinate of your vertex. Opposite of b over 2 times a. Yep. Negative 4 over 4. That's negative 1. Okay. So we've got the x coordinate of our vertex. How would we get the y coordinate of our vertex? Plug it back in. So that'd be 2, so y equals 2 times negative 1 squared plus 4 times negative 1 plus 2. Take your time on this. You have to do the exponent first. Negative 1 squared is positive 1 times 2, so that's 2 minus 4 plus 2 what do we get? 0? Okay, that's interesting. Because if I go to my graph and I graph this function, -1, 0, and I'm graphing 2x squared plus 4x plus 2, I can use my a value of 2 to vertically stretch. So instead of going up 1 over 1, I would go up 2 over 1. Or I can use my y-intercept. Where should my y-intercept be? 2. But that confirms like both. Up 2 over 1, I've stretched it vertically, or I used my y-intercept. Reflect over my axis of symmetry. Okay, there's my graph. Well, if you're trying to solve the equation, what's your answer? X equals -1. When was the function equal to 0? At the vertex. Right? My vertex is sitting on my x-axis. So in this case, the only point of my parabola that makes my function equal 0 is when x equals -1. So like even before I graphed, I kind of knew that was going to be my answer, right? But I wanted to finish out the graph just to show you like there's no other place that the function equals 0 because the u is opening up. So solve the equation up there. The solution is x equals -1. Now remember, we first made that equal to 0 so that we could graph it and look for x-intercepts. But in this original equation, I could do a quick algebraic check if I'm saying x equals -1 is the answer. -2 times -1 squared minus 2 should equal whatever 4 times -1 is. So like the two sides aren't necessarily 0 in the original problem, but because I just subtracted or added those two terms to the other side, it should be the same thing. This would be -2 minus 2, so that would be -4 on the left, and then this will be -4 on the right. So is -1 the one that works? Yeah. Just kind of confirms. Remember again, I like math when it all, like, no matter which way I do it, it's still working. Okay, whether I made the equation equal to 0 or I plug it back into the original equation, the two sides are equal. And that's the only number that's going to do that.
How did you get the y-intercept?
The y-intercept, if I'm looking at this ax squared plus bx plus c, c is the y-intercept. 0c. If you go back to your notes in standard form, we said we would find the y-intercept for that one, and it was always 0, c. Because if you put 0 in for the x terms, they disappear, and all you're left with is the constant. This is kind of like a shortcut to getting an extra point, but I like that a lot. Good question. Okay, now can you imagine some other parabolas where you would have more than one answer because you would have more than one x-intercept? Could you imagine a parabola like that? Yeah. Okay, so I could make one up really fast. Okay, just to kind of like illustrate. Let's see, I'll do 0 equals, I'll do negative quantity x minus 3 squared plus 1. Okay, where's its vertex? 3, 1. Remember, h always looks like the opposite. Excellent. Right 3, up 1. On this one, that k value is part of the vertex. That's not my y-intercept. That's only for standard form. So we were taught to graph with our a value. So since a is negative, there's a reflection. in the x-axis, but it's -1, so there's no stretch or shrink. So I can follow the patterns of the parent graph. Just go down 1 and down 4 if I want an extra point. So I could go down 1, right 1. I could go down 4, I'll be at -3, right 2 if I want an extra point. And then of course I could reflect over my axis of symmetry. Can you tell me when that function equals 0? For what x's? Your solutions will look like x-intercepts, Kenzie? Close? That first one again.
Oh,
2. So we're looking, where are the solutions going to be located? At your x-intercepts, right? Like this point is 4, 0, and this point is, oops, I almost wrote 2 there. I mean 1. That point is 2, 0, so the solution to this problem is x equals 2 and x equals 4. You have 2 answers because you have 2 x-intercepts. On the first one, we had 1 answer because we turned on the x-axis. And then if you wanted to check your answers, you could plug those things in, right? So like 2 minus 3 is -1. Quantity squared would be a positive 1. But then there's a negative in front of it, so it would be -1 plus 1, which is 0. And it makes the statement true. Can you imagine? So we've seen an example where we have 1 solution. We've seen an example where we have 2 solutions because we cross the x-axis 2 times. What's the other possible number of solutions?
Or infinitely many.
Not infinitely many. The parabola turns once, right? So its arms can cross twice. It never turns around again. No solution. What would the parabola look like so that there was no solution?
The points are like after the x.
What do you mean? The points are
So,
after the x.
Well, like the vertex is above or under.
Okay, so if the vertex was above, what would your parabola have to do? It would have to open up. Will you ever be able to tell me when that function equals 0? Not right now. Someday, yes. When I teach you about imaginary numbers, numbers that exist but are not real. Ooh, sounds exciting, right? Or you could have a picture where the vertex is below, like Delaney said, and the parabola opens down. But then you have no solution. So how many solutions you have is going to depend on the picture of the graph.
Does that depend on what equation you use also?
No, any one of the equations could model these graphs. So I could use vertex form. I would have a vertex HK that is going to put me in this like upper area, and then my A has to be positive. Or it could, the only one that wouldn't work on these would be intercept form. I wouldn't give it to you in intercept form because it doesn't have intercepts. Okay. Okay. So just some food for thought, thinking about like how many and what type of solutions. I have no solution. Put this. 2 solutions. And in the first one we had 1 solution. So we now have 3 cases of types of solution. Okay, so the next one we're going to get into is solve by taking square roots, which this is reverse PEMDAS. And this is where we get into like the real algebra parts. We're not just doing the graphing. Because can you imagine this? Think in your head. You graph the parabola, you find the vertex, you use like a stretch or shrink or an A value or an intercept or something like that. But the place where it crosses the x-axis is not a nice number. Like it's not one of the points you plot. Could you imagine that? Like if I had taken that vertex form problem if I had put a +2, then we would be moved up 1, and neither of these points that I graphed so nicely would cross the x-axis or be on the x-axis. So we need to have other methods besides graphing, because what if your point isn't a nice point? What if it's in between two values, two lattice points on the graph? Okay, and that's where the rest of chapter 3 goes. How do you find all the solutions algebraically so you don't have to do this graph every time, so that you can get the exact values even if it doesn't cross at a nice point? So now we're going to do solve by taking square roots. Okay, I'm going to give this to you in your groups. 2/3 x squared plus 14 equals 20. And I'm going to see what you guys can come up with. So if I told you to solve for x, so think about like in Algebra 1. If you want to solve for x, you want to get x all by itself. Isolate x. Talk to your group members. What might you do to get the x alone?
Subtract 14 and multiply by the reciprocal.
Yeah.
Which number I want to get rid of?
Yeah.
Eat my sandwich.
I'm hearing good conversations and I'm seeing good work. Most groups say subtract 14 first. So we'll get 2/3 x squared equals 6. Okay, how did your groups tackle the rest of that problem, Maddie?
We multiplied it by 3 over 2 because that's the same as like dividing by 2/3.
Ooh, I love what you said. She multiplied by the reciprocal 3 over 2 because that's the same as dividing by 2/3. Excellent, right? If you divide by a fraction, you're multiplying by its reciprocal. Okay, and that kind of kills two birds with one stone. You could multiply by 3 and then divide by 2, like in 2 separate steps if you wanted to. But this one works out pretty nicely. So you have x squared equals, and this would just be 18 over 2, which is 9. Now, if it came out to be a fraction, I'd leave it as a fraction. I'll say generally we want our answers to be in exact form, not rounded form. That's preparing you for pre-calculus and calculus, where your teachers want exact answers. Okay. So you for some of this stuff, I say put your calculator away. Don't get too calculator happy. And like when you're simplifying, leave things as fractions or radicals. Okay, and then last step was square root both sides. So what did you guys all get for your answer? X equals 3 or negative 3. Okay, excellent. So that's something different because we're all coming from, well, most of us are coming from geometry. So that's something different than geometry. Like you solved a lot of things that were actually quadratic. They were the Pythagorean theorem, ax squared plus b, or sorry, not ax squared. Stuck on algebra. A squared plus b squared equals c squared. So you did a lot of like square rooting in geometry. But in algebra, when you square root to solve, add a plus or minus. If I could star, circle, highlight, study, remind, say out loud, I would do all those things. In geometry, you left off the negative because you were often finding like side lengths in the Pythagorean theorem, and a negative side length wouldn't make sense. But in algebra, we're just saying like, what are the x's that make this statement true? Well, it could have been a positive 3, or it could have been a negative 3. Because when we put them back into this equation, we end up squaring them right away, and they would both equal a positive 9. And a positive 9 times 2/3 would be 18 over 3, which is 6. And 6 plus 14 would equal 20. So the negative 3 and the 3 are going to work. So this is an example. How many solutions do you have? 2 solutions. And what would those solutions look like on your graph? They would be the x-intercepts. Okay, so this one we probably could have solved by graphing because it came out to a nice number. Okay, let's look at the second one. 2 times the quantity x minus 4 squared minus 9 equals 1. So when I look at that one looks a lot like vertex form. I could have also seen this one as vertex form if h were 0. Then this would have been my k. You could also see it as standard form like ax squared, but then the b is 0, so plus 0x plus c. So it doesn't really matter which form it is. Okay. But if we were looking at this one, we would solve much the same way. First step, add 9. Next step,
I did the exponent, so what I did is I wrote it out like 2.
you could, but that's making a lot more work. Because at that point, you're doing stuff on the side with x, when if you're trying to solve for x, your whole goal is to move things to the other side. So like, it is a valid way to solve, but like you would need perhaps factoring, completing the square, or quadratic formula, which we haven't studied yet. So I'm going to go back to your statement here in just a little bit.
So would you like divide by 2?
I would divide by 2. First of all, I love what May said. She was going to write it out as x minus 4 times x minus 4 and FOIL it out. Okay, it is not x squared plus 16. Cannot distribute an exponent into a parentheses. Let's be aware of that. And then you also can't distribute the 2 into the parentheses because it has an exponent. You can distribute 2 if there was no exponent. But because that thing is being squared, we can't distribute the 2. And that goes against like our whole goal of isolating x. We're trying to like peel away the things from x, not do more stuff to x. So we want to move it to the other side. So I like what she said. Divide by 2. So what does this give me? 5? And then I can do what? Square root. Star, circle, highlight, note. When you square to solve, you better add a plus or minus. So now I just have x minus 4. It cancels out the square. It doesn't square root anything in that parentheses. Okay, it's just undoing the square. So we have x minus 4 equals plus or minus square root 5. I'm fine with that. We'll talk about simplifying some radicals as we go through this chapter. Leave it in radical form because this is exact. If you type square root 5 in your calculator, you're probably getting 2.1 or 2.2. But we want it exact, not rounded. Okay, and then last step would be add 4. Now here's how we're learning how to write things so that they're going to look like quadratic formula. You're always going to put that thing in front of the plus or minus. Okay, so x equals 4 plus or minus square root 5. Now, you have how many answers there? 2. Your 2 answers, 2 solutions, are x equals 4 plus the square root of 5 and x equals 4 minus the square root of 5. I'm okay with you leaving it as 4 plus or minus square root of 5. Just know that you have found 2. And then, what would those points be on your graph? X-intercepts, okay? And so if they were x-intercepts on your graph and you were trying to draw a graph for this quadratic, you would actually want to like evaluate that. So, if the square root of 5 is approximately, I'm not sure what it is, let's estimate it at 2.1 because it's a little over the square root of 4. Then I could say one answer is 4 plus 2.1. I have an x-intercept a little bit past 6. And x equals 4 minus 2.1, so an intercept really close to 2, but not quite 2. So those would be x-intercepts on the graph if you wanted to plot them. 6.1, 0, and 1.9, for graphing purposes. But most of the time when I'm asking you to do this solving in chapter 3, I'm not going to have you also graph it at the end. I just want this answer 4 plus or minus square root 5. Now, if you're answering a question, like a real life question, an application question, and it's like wanting to know like how many feet something is, well then you're probably not going to include anything that would be negative, right? And you probably want to like evaluate it so that it makes sense. Like you need 6.1 feet of fencing. Okay, you don't want to tell someone to go to Menards and pick up 4 plus square root 5 feet of fencing. Okay, then you give the rounded answer. But generally, if it's just a workout problem, leave it in exact form. Okay, anybody got any questions for me? All right, your homework assignment is on page 99. Here you go, Mo, take this gold sheet. Got a little joke for you. Found it when searching my memes. Oh, wait. Does anybody know what the answer is? I thought I was showing it already. What do baby parabolas drink? We're not there yet, but you might have learned it in Algebra 1. Quadratic formula. Babies drink formula sometimes. We'll get there. Quadratic formula is the last section in the chapter. But have you guys learned the quadratic